I'm Algebra Annie, and I am here to help you be successful in your algebra class. Mistakes are proof that you are trying. Unknown. Our learning targets today are: I can solve special systems of linear equations in two variables. I can classify systems of linear equations and determine the number of solutions.
Now we're solving special systems. So far in this chapter, everything has been about solving a system of equations. And you're always given a system that has an equation for a line 1, an equation for a line 2. Now what is the whole point of solving the system? What are we actually looking for? When you're solving the system, you're trying to find where do these two lines intersect? That's the whole point. Solve the system is you asking, where do these two lines intersect? In all the problems we've done in the past, if you had line 1, you would then be able to find a point where line 2 would have crossed, and their point of intersection would have been the answer as an XY coordinate point. Well, is this the only way that two lines can be drawn on a coordinate point? We already know that this is one possible way that two lines can be drawn. So in this example, you always got one answer. If I drew a line, now is there a way that you could draw the second line to where there would be no answer, which means that they would not intersect? Can you think of two lines that never intersect? Well, in a previous chapter, we learned that parallel lines will never, never, never intersect. So I can draw line 2 such that it would never cross line 1, which means we would never have an answer and it would never intersect. If it never intersects, you're never going to find a point of intersection, which means you have no solution to a system of equations. Well, are these the only options that we have available to us? So we have 0 points of intersection and we have 1 point of intersection. Can you draw line 2 so that it has a lot of points of intersection? Now remember, it has to be a straight line. If I draw line number 2 right on top of line number 1, it has every single point in common. Since the lines go on infinitely in both directions, that means they have infinitely many points in common. What do all three of these answers look like depending on how you were asked to solve your problem? So we have a system of equations, and we're told that this system of equations has no solution. Well, remembering to the three graphs we just looked at, if it has no solution, that meant that it does not intersect. What do we know about two lines that never intersect? I know that parallel lines will never intersect. So we know that these are supposed to be parallel. How can we determine that? Looking at just the slopes and the y-intercepts. So we're going to do that by just looking at the equations. So let's look at equation number 1 and compare that against equation number 2. So equation number 1 was y equals x minus 1. Equation number 2 is negative x plus y equals 2. Remembering, I cannot compare slopes and intercepts unless it is written in y equals mx plus b form. I needed to get it into y equals form. Equation number 1 is written in y equals mx plus b form. So I can identify my y-intercept and I can identify my slope. The y-intercept is b. b is going to be my negative 1. Slope is the number in front of x. My number in front of x is 1. Well, I need to be able to compare this to line 2. Line 2 is not in a y equals form, so I need to do algebra, which means I need to add x to each side. So I get y to equal x plus 2. Now that it is in y equals mx plus b form, I can identify my y-intercept and I can identify my slope. The y-intercept is the b of 2. My slope is the number in front of x, which is 1. What do you notice about the y-intercepts and the slopes? I notice that my slopes are the same. So I notice that I have the same slopes. Are my intercepts the same? They're not. So I have different y-intercepts. So if I were just to compare equations, and I was asked how many solutions would this system have, if I noticed they had the same exact slope but different y-intercepts, I would know then they were parallel lines And I know that parallel lines have no solution. And so I would list off all those answers. Because the slopes are the same, but the y-intercepts are different, I know that they are going to be parallel. And if they're parallel, they'll have no solution. So I just showed that these are parallel and they have no solution because the slopes are the same and the intercepts are different. Same exact problem. If I was asked to find the solution to these, what would it look like on a piece of graph paper? So if I'm graphing it, I need to graph line number 1. Line number 1 was y equals x minus 2. Remembering, if I am graphing, it needs to be in y equals mx plus b form to be able to graph it. This is in y equals mx plus b form, so I can graph it. To be able to graph, I need to know what my y-intercept and my slopes are. My y-intercept is the b, which is a -1. My slope is the number in front of x, which is 1. So my y-intercept is -1. My slope is up 1 over 1, up 1 over 1, up 1 over 1. I like to do many, many points. The more points I have, the more perfect my line is going to be. Grab your ruler, connect our points. Remembering, you need arrows on both sides. So that's line number 1. We need 2 lines because there's 2 lines in our system. So line number 2 is the equation -x plus y equals 2. It needs to be in y equals mx plus b form to be graphable. He's not in y equals form. So I need to add x to both sides. Y equals x plus 2. Now that it is in y equals mx plus b form, I can identify my intercept and I can identify my slope. My y-intercept is the b, which is 2. My slope is the number in front of x, which is 1. So my y-intercept starts at 2. My slope tells me to go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. I keep going. The more points I have, the better. Connect them with a line. Now, just because they do not connect on the graph paper that you are looking at doesn't mean they won't connect way out here or way out here. So you need to check and see. How can you prove that these are actually parallel to one another? If you look at the distance apart, let's see, that is 1, 2, 3 spaces apart, 1, 2, 3 spaces apart, 1, 2, 3 spaces apart, 1, 2. It looks like these 2 lines are always going to be 3 spaces apart. Since the lines are not getting closer together at all, then these lines are never going to intersect because they're never getting closer. If they're never getting closer, then you know that these lines are parallel. Lines are not getting closer. If the lines are not getting closer, then you know that they are parallel. And if they're parallel, they are not going to intersect. And if they're not going to intersect, you know that there is no solution. And that would be your thought process to prove, I graphed these. I was supposed to find somewhere where they intersect. They must never intersect because they're parallel. So there's not going to be a solution. Same exact problem. What if your teacher told you you had to solve this system of equations and you had to solve it using either substitution or using elimination? What would your answer look like then? So looking at this, because I have y equals, I'm going to go ahead and use substitution. Substitution is really easy and simple to use if you already have an equation that is a variable equal. So I'm going to use the first equation as my beginning equation. So y equals x minus 1. If I know that y equals x minus 1, that meant that in the equation that I have not used yet, my y should not exist because you just said that y was all of this. So I should be writing all of this instead of my y. So I have, negative x plus all of what y you said was x minus 1 equals 2. I see there's only one variable left. All I see is x's, so I'm going to solve for my x's. So I'm going to get rid of this parentheses by distributing this positive. A negative x plus x cancels out to 0, so I'm left with just negative 1 equals 2. Back in chapter 2, we learned what happened when your variables disappeared. We're supposed to check to see if the statement's true or not. This statement is not true. Negative 1 is not equal to 2. You learned back in chapter 2, if this is not true, then you knew that there was no solution. We now know if there's not a solution, you know that these lines are going to be parallel lines. Finally, a new problem. We have a brand new system of equations. They're telling us right off the bat that this system of equations is going to have infinitely many points, which we now know means that we're going to draw two lines, and both lines are going to be in the exact same spot on our piece of graph paper. So what would this look like if we were actually comparing equations to one another? So if I look at equation number 1 and if I look at equation number 2, equation number 1 was y equals 2x plus 1. Equation number 2 is 2x minus y plus 1 equals 0. I am not able to compare slopes and intercepts unless my equation is written in y equals mx plus b form. Equation number 1 is. So I'm going to identify my y-intercept and I'm going to identify my slope. My y-intercept is the b, which is a positive 1. My slope is a 2. Now I need to know what the slope and intercept are of line number 2 so I can compare. This is not in y equals form, so I need to make it in y equals form. So I'm going to add y to both sides. I get 2x plus 1 to equal y. So this is actually y equals 2x plus 1. I can now find my y-intercept and I can now find my slope. The y-intercept is the b of a positive 1. My slope is the number in front of x, which is a 2. Now we're being asked to compare our slopes and our intercepts. I notice my y-intercepts are both 1. I notice my slopes are both 2. So my intercepts are the same, my slopes are the same. Well, if you look even closer, what a coincidence, what a coinky-dink. My equations of the line are actually the same as well. Since this was such a coinky-dink, we actually call these coincident lines because what a coincidence, the two lines are actually the same line. These are coincidence lines. And they're coincidence lines because their y-intercepts are the same. Oops. Because their y-intercepts are the same and their slopes are the same. What a coincidence. They were the same line. And since they're the same exact line, they share every single point. That means that there are infinitely many solutions. So what a coinky-dink. We had two of the same exact line. So they're called coincident lines because they're the same line. So very same question. Solve this system of equations, but solve it by graphing. What would it look like to have two graphed lines and they were infinitely many solutions? So let's go ahead and check this out. So to graph it, I need to look at equation number 1, which is y equals 2x plus 1. This is in y equals mx plus b form, so I can graph this one immediately. My y-intercept is the b of 1. My slope is the number in front of x, which is 2. So my y-intercept of 1, slope is up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. I am going to go ahead and connect these. Remember, if you're connecting it with the line, you need arrows on both ends. Well, that was only line number 1. I need two lines. So line number 2 is 2x minus y plus 1 equals 0. This is not in y equals mx plus b form. I can't graph it yet. So I need to do algebra to my equation. 2x plus y equals 1 equals y. So y equals 2x plus 1 is my equation. I need to know my y-intercept and I need to know my slope so I can graph it. My y-intercept is the b of 1. My slope is the x of 2. New line, new color. Y-intercept is 1. Slope is up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. Since I'm using a different color, I can actually see now that I had two lines drawn, and those two lines were actually drawn right on top of one another. So they were in the exact same location. They share every single point that they have in common. So yes, these are the same exact line drawn on the graph. They share every single point. If they share every single point, that means that there are infinitely many solutions. And what a coinkydink! They were the same line. So we actually call these coincident lines. Now what if you were asked to solve the same exact system of equations, but this time your teacher did not tell you anything. They asked you to solve it by either substitution or elimination. What would your answer look like then? So since I have a variable equals, I know that substitution is going to be the easiest method to go. So I'm going to pick that one to start with. So y is supposed to equal 2x plus 1. If I know for a fact that y equals 2x plus 1, then in the other equation that I have not done yet, y should not exist. Instead of having y, this y, I should write all of this because you told me that's what y was. So this is 2x minus the entire quantity of y, and since it is the entire quantity of y, it needs to be in parentheses. The rest of the equation is the same. I see only letters of x still left, so I'm going to solve for x. So I need to distribute this negative sign to everybody in the parenthesis. This 2x was not a part of the parentheses, so he's still 2x. Negative times 2x is a negative 2x. Negative times a positive 1 is a negative 1. That was a positive 1 equals 0. If I had 2x's and I took away those 2x's, those disappeared, so that's 0. A negative 1 plus 1 disappears. I'm left with just 0. So this entire side, everything cancels out to 0, and my right side was always 0. Remember it in Chapter 2, solving equations. If your variables all canceled out and you were left with a mathematical statement, you have to judge, is this statement true or not? This statement is true. Now, if you remember, back in Chapter 2, if your statement was all true, you would have written all real numbers. If all of my numbers are a solution, how many solutions did I have? I had infinitely many solutions. If I had infinitely many solutions, that meant that these were the same line. And what a coinkydink. If they're the same line, they are coincident lines. Then you're done. So we have this table that basically summarizes everything that we've learned. You could have a line that intersects just in one spot, and then you would have exactly one answer. We looked at the slopes and the intercepts for this, and we noticed that this happened when we had different slopes. If you have to classify these, you would then classify these type of equations as consistent and independent. Now, what a coinkydink. They're the same exact lines. They were coincident lines. If they're the same exact line, they shared everything in common because they're the same line. They had the same slope. They had the same intercept. They had every point in common, so they had infinitely many solutions. There's actually two lines right there. If we had to classify that, you would classify that as consistent and dependent. The other one we learned about, we had two parallel lines, which means they're never, ever, ever going to intersect. If they're never, ever, ever going to intersect, you will never have a solution. And you know from a previous chapter, if they are parallel, they have the same exact slope. That's the definition of parallel. Now, if your lines are parallel, you would classify him as inconsistent. So our next few problems, we're going to get a system, and you have to tell me which of these three categories does our system fall into. So we have two equations, and I need to split them right down the middle. So this problem right here, I was given a system of equations. I want to know how to classify it and how many solutions are they actually going to have. I want to know which of those three categories would this fall into. So I'm going to just go ahead and compare my slopes and my intercepts and see if I can decide, do they have one intersection, no intersections, or do they have all of the intersections? So let's go ahead and look at this. So I'm going to compare, I'm going to choose to compare slopes and intercepts. So equation number 1 is 2y equals x plus 1. This is not a y equals mx plus b. So I need to divide everything by 2. I get y to equal 1/2 x plus 1. So I can identify my y-intercept and I can identify my slope. The slope is a 1/2. My y-intercept was a 1. I need to be able to compare it to line 2. Line 2 is a negative 1/2 x plus y equals 1. It needs to be in y equals form for me to be able to compare. So I'm going to add a 1/2 x to each side. I get y to equal 1/2 x plus 1. So if I compare my y-intercept, which is a 1, and my slope, which is a 1/2, let's see what we got. I see that my intercepts are the exact same. I see my slopes are the exact same. They share everything in common. And if I'm looking at it, what do you know? What a coinky-dink. They're the exact same lines. So how do I classify the system? Well, if they're the exact same system, I know that they're coincident lines. If they're coincidence lines, how many solutions did they actually have? They had infinitely many solutions. But now I need to classify it. So looking back at our old chart, coincident lines, infinitely many solutions. What is his classification? It is consistent and dependent. So we would classify this system of equations as consistent and dependent. And you would need all 3 answers to answer this one problem. Doing the same exact thing for the second equation. Since this one was comparing our slopes and our intercepts, I'm going to do this one by substitution. So I want to go ahead and substitute. So I'm going to go ahead and pick this equation right here as my first. So y equals x plus 1. If I know that y equals all of this, then that meant in the equation that I have not used at all yet, my y should not exist. You said y was all this. So this y should actually be him. So x plus 1 equals 2 times the parenthesis of x minus 1. I'm trying to find where they intersect. So my x's, I need to distribute my 2. So I have x plus 1 equaling 2x minus 2. I need to solve for x. I'm going to subtract x from each side. I get 1 to equal 1x minus 2. Add 2 to each side. I get 3 to equal x. I found an answer. If I look like I'm starting to find my answer, then how many locations will they cross at? If I found something, then I know immediately I'm going to find my one answer where they intersect. So this has one answer, which meant these do actually intersect. These are intersecting lines. And if they're intersecting lines, one answer. Let's go ahead and check our chart. My intersecting lines had exactly one answer. What would you classify it as? Consistent and independent. So this is going to classify as consistent and independent. And you would need all 3 answers. And you're done.
What did we learn today? I can solve special systems of linear equations in 2 variables. I can classify systems of linear equations and determine the number of solutions. And I look forward to seeing you tomorrow in class.